The title of this presentation is Anchoring Parallel Repetition and the Relative-Min Entropy, Decay of the Optimal Value. I first wanted to begin with a couple of slides which are going to highlight some of the previous remarks and the high points, so to speak, or the general remarks from the first presentation in the series, the previous presentation. Namely, the fact that I was trying to draw the attention of the viewer to the fact that there are a lot of connections with some previous works from statistical physics and quantum physics and mathematical physics, which are informing our efforts in studying dependency breaking variables and how to actually remove quantum correlations, which would hence give us some ability to be able to view quantum decoherence as well as the implications for the winning probability of different multiplayer game theoretic settings. And in particular, as the viewer can recall, I drew the attention of his or her attention to the fact that there are many types of applications from work that I've currently submitted at a variety of journals, which are relating to either the random field Potts model and the correlation lower bound, various aspects of vertex models, whether it be relating to logarithmic localization of the height function or crossing probability estimates for other types of models of statistical physics, which can be placed into correspondence with the six vertex model, as well as even Poisson structure and how that relates to the quantum inverse scattering method, amongst a wide variety of other topics, some of which can relate to seminal work on Bernoulli percolation from Keston, in which he was establishing, demonstrating how to make use of dependency of long crossings of Bernoulli percolation into shorter crossings, and how that can even relate to phase transitions in the seminal Pauwels argument. Also, the viewer will recall that there were previous works in quantum physics which I also drew their attention to, namely the fact that in the first or in one of my earlier works in quantum physics, one of my first works, I discussed about how to make use of game theoretic settings for two-player quantum games, namely through the XOR star and the FFL games, and in being able to characterize optimal and approximately optimal quantum strategies, and how in fact these general notions of optimality or near optimality can be factored into quantum states and the bias and the expectation, different types of basically values that one can expect and be able to compute from, two-player settings and multiplayer game theoretic quantum settings alike. And this was really relating to the fact that I had first more been introduced into the field of quantum physics and information processing from more of an algorithmic type of perspective, because I really looked at in this work for a variational quantum algorithm for measurement extraction. It's a pretty old paper. I mean, I guess for me, it's from 2022, a couple of years ago, which is quite a long time ago already, in which basically I was looking how to adapt a variational quantum algorithm, which is relating to just a generalization of the variational quantum eigensolver, which can be used to basically formulate cost functions for partial differential equations and being able to solve them and moreover, also more importantly, to accommodate a wide variety of initial conditions for these highly nonlinear and complicated systems, depending upon the initial starting point of the quantum algorithm through the ansatz. And then more recently this year, in 2025, I've been looking at quantum strategies, error bounds, optimality, and duality gaps for a wide variety of multiplayer settings, in addition to the fact from my most recent preprint on the archive from, like 4 or 5 weeks ago, for which was primarily relating to the distribution and the transmission of classical information over quantum channels through the paper, through the preprint that's currently under peer review, error correction, authentication, and false acceptance probabilities for communication over noisy quantum channels. And again, the viewer can gather and surmise from these types of works I've been talking about it's still of great interest not only for me but for many researchers in the field of quantum information processing and quantum information processing tasks and algorithms to be able to determine what is the effect of the optimal value, namely the supremum of the winning probabilities for either a multiplayer setting or a two-player setting, which is resulting from the fact that the questions which are distributed to each one of these players from the referee's probability distribution takes the following form. Namely, if we're looking at the question set raised to the tensor product of little k times, where little k times is the number of times that we're performing parallel repetition for some multiplayer game or a game with an arbitrary number of participants or an arbitrary number of players. It's given by the fact that we're having tuples for each one of the questions corresponding to the questions that are distributed from a countably many number of possibilities from the referee's probability distribution to each one of the participants. And it's given by a tuple of the question set for the first parallel repetition, the first instance, up to the kth round or the kth instance, a parallel repetition for each one of the questions that are distributed to each one of the players and the participants. And again, it really comes into the fact that for the first preprint on multiplayer quantum games that I had from May of this year, I believe May 8th is when I first submitted it to the archive. That this preprint is also currently under peer review as well somewhere else. I was really heavily making use of and heavily relying upon the fact that parallel repetition, it has a very different type of and even paradoxical and unexpected consequence on the optimal value of the game, namely the fact that despite the fact that the probabilities for assignment of different answers from questions that are distributed from the players from the referee's probability distribution are almost the same because in the XOR game, this certain probability that's different from the one in the FFL game is a half versus a quarter. This actually results in a very different and almost opposite type of behavior with regards to the operation of parallel repetition on the optimal value, namely, hence on the supremum of the winning probability for some game. And this is given by the fact that two rounds of parallel repetition for the XOR game, whether it's two-player XOR game or multiplayer XOR game with an arbitrary number of participants, is given by the fact that it's equal to the product of individual copies of the the supremum of the winning probabilities, hence the maximum winning probability for the XOR game, which is equal to 1/2, which is not equal to 1 over square root of 2, which is the original value of the optimal value, hence of the winning probability of the XOR game before performing parallel repetition. However, like I've been mentioning, why I wanted to mention why there's only a difference of the probability of one assignment of an answer for one question for one player from some question that's drawn uniformly at random from the referee's probability distribution is the fact that there's an invariance of parallel repetition for the optimal value of the FFL game, namely that, again, like we have been mentioning, we have been closing out in the previous presentation of this series, it's such a it's such an interesting type of sorry. It's an interesting type of connection to keep in mind because it's demonstrating how performing the operation of parallel repetition or strong parallel repetition for the FFL game leads the value of the largest probability of winning invariant. Namely, it's equal to 2/3 before and after performing this operation of parallel repetition, which is not equal to the square of 2/3 as it was for the optimal value of the XOR game. And again, we closed out some of the with a very broad and general overview with a statement of three of the important theorems which are going to be used to build up to a result for the decay of the optimal value under anchored parallel repetition. And in this presentation, the second presentation of the series, what I was going to do was I was going to draw the attention of the viewer more towards what exactly is anchoring and how this differs from how this distinguishes ordinary parallel repetition and anchored parallel repetition. And in fact, like I've been mentioning to the viewer and describing in the previous presentation in the series, it's related to the fact that there's a computational complexity type interpretation, which very much is very important, of great importance, and of great interest for many researchers in quantum computing and quantum information processing and quantum information theory, because we're always trying to determine whether there could be some polynomial speed up. And of course, there are still a lot of people who kind of live in, I guess, less of a realistic type of world, and they expect that every type of quantum algorithm is going to lead to some exponential speed up, which probably is far, far from the case. That probably, maybe, unfortunately, more of the industry may have to come to grips with soon in a couple of years as we're reaching more fundamental roadblocks in terms of how many qubits can be scaled reliably for noise for fault tolerant in noisy computation on your quantum devices during the NISQ era. And in particular, in this game theoretic type of situation that I've been describing for the viewer, it's really relating to the fact that we're looking at how to upper bound, in fact, some system of expectation values. Now, recall from the previous presentation in this series, I didn't really exactly describe to the viewer right off the bat, what the system of expectation values are, because I'm going to spend the next couple of presentations and devote a lot of attention towards where the system of expectation values comes up from and what is the game theoretic interpretation of such values. But we can just see that basically these three results, like I've been describing for the viewer in the previous presentation of the series on the slide, they have to relate to either upper bounding with some big O notation, which is really demonstrating some type of computational complexity result, because it's just basically saying that the guarantee of being able to compute these expectation values that I'm going to be describing more for the viewer, it's upper bounded by some constant times this function. And all these functions are given, like we see in theorem one, quantifying the largest order of the system of expected values with normalization factors, where I'm going to be getting more into the normalization factors and their uses in the remaining presentations in the series. It's related to some upper bound of some fraction of delta multiplayer raised to some fraction, which is dependent on the number of players n, big N, for an arbitrary number of players in multiplayer game theoretic quantum settings, as well as being normalized by the multiplayer anchoring probability. So again, I'm going to first be able to describe more what's the anchoring probability for the two-player setting and how that would relate to some multiplayer type of generalization of this quantity. And furthermore related, we can see in theorem two that it really has to relate towards quantifying the largest order of the POVM system of expected values. And like I briefly mentioned for the viewer in the previous presentation of this series, the POVM stands for positive operator value measurement. And like I mentioned, it's being able to describe in a different type of way, in more of an explicit sense in comparison to some quantum information processing papers that I've been having this year, is basically a way to bridge and define traces of tensor product representations in terms of probabilities. So that really was something that was very interesting for me to explore, because I'm really more of a discrete probabilist, and it's really interesting to be able to bridge that gap between maybe discrete or continuous probability and information processing. And that's really what I'm hoping to make apparent, that really, even though a lot of people, maybe someone who's interested in this type of area study, they may see a lot of more general audience presentations which are talking about quantum physics and probability, but this is really providing a more specific mathematical structure within positive operator value measurements, and how quantum mechanics, which is ultimately relying upon taking measurements and being able to extract meaningful measurements, like I described in my paper, in one of my older papers that's also currently under peer review in a computational mathematics journal, how this is actually relating to basically being able to define this in terms of probabilistic quantities. And finally, in the third result, theorem three, like we talked about, we were describing how to quantify the largest system of expected values with Pinskers inequality. And Pinskers inequality, it's an inequality which is used to upper bound the L1 norm between two quantum states in terms of the relative entropy. So again, this shouldn't come as a surprise that entropy it's coming into play, especially given some previous results I described from a project of mine from this year for the bit transmission rate, which is ultimately relating mutual information entropy to conditional Shannon entropy, and in fact how the mutual information entropy is used to now in this work establish connections between the relative and the relative min entropies, which I'm going to be describing further in this presentation. And so I'm going to provide an overview now that we had kind of discussed some very broad strokes and reiterated some talking points from the first presentation of this series, and what are the implications for quantum information processing. And this is basically given by the fact that we're further building upon our discussion of quantum games from the previous presentation, some of these points which I've been describing for the viewer, including the sets of dependency breaking variables, the relative min entropy, anchoring, and parallel repetition. And we're actually, in comparison to the other multiplayer game theoretic settings that I've been describing for the viewer in the previous presentation, we're really going to describe how to mesh and how to incorporate simultaneously aspects of anchoring and parallel repetition simultaneously with anchored parallel repetition. And altogether, our goal for this presentation, the second presentation of this series, will be to further discuss how computations with the entropy determine upper bounds for the POVM system, the positive operator value measurement system, which is inherently really a probabilistic system, which is relating to the probability measure with respect to the expectation values that we're going to compute in the other two results, namely the result that we're going to describe in very briefly, describe later on in the presentations in the series, how to upper bound using Pinsker inequality, as well as the first system of expectation values that's given in Theorem 1. So this is really the original part. So I'm going to appeal more to probabilities and discrete probability in particular in this presentation of this series so that we can really demonstrate and elicit more of those connections with statistical physics and quantum physics and quantum information theory and quantum information processing. And so what I think a great type of approximation or probabilistic statement to begin this presentation of the series that we can use to discuss more dependency breaking and its connections with symmetry breaking in a quantum sense is the fact that we're looking at the probability of sampling A sub I and B sub I conditionally upon the fact this conditional probability, given the fact that the set of all questions that are distributed to the first player in this two-player game theoretic setting is little x, as well as the question that's distributed to the second player from the referee's probability distribution is little y. Also conditionally upon the fact that we're conditioning that W sub c holds. And W sub C holds, I'm sorry, this is a little typo to the viewer, but this should be a big C here because it's going to appear as a big C in all of the other parts of the presentation. I apologize for that. But basically, it's the probability or the event that the player wins across all coordinates. And why we're looking at this winning probability, and very often in these types of probabilistic arguments, discrete probabilistic arguments, we're incorporating this into the conditioning is because we're looking at whether some player would be able to win the game across all rounds of parallel repetition. Because what we're basically doing, like I demonstrated to the player or to the viewer in a previous slide from the first presentation, is that when we're looking to perform parallel repetition, what we're doing is that we're raising some questions to some tensor product power. And what this is allowing us to do is just basically determine whether the probability of winning across all rounds of parallel repetition can be expressed and can be formulated in terms of winning, probabilistically speaking, across all one of the components or component-wise of the tuple for the questions that are distributed to each player from the referee's probability distribution. And throughout the field of quantum information processing, there's a lot of symbols that are typically used for either aborting an information processing procedure or in this case for anchoring. And this is actually getting more into what is anchoring and how it actually impacts the individual questions and how it results in removing quantum correlations from some system. And this is given by the fact that we're looking at setting or introducing anchoring for the question that's distributed to the first player with this bot symbol, which is given by the first symbol, which we're setting identically equal to x sub I in the conditioning of this probability in comparison to the original probability that we started out in the left-hand side of this approximation, in which we had the question set to little x and little y respectively. So we're basically guaranteeing, probabilistically speaking, that this probability of sampling some answer or some response from each one of the two players in the two-player game theoretic setting would not change so much if we just set one of the questions to some anchored response for the first player, while keeping the response or the question that's distributed from the referee's probability distribution for the second player to be the same. And this is even the same in the sense that we actually even furthermore want to be able to guarantee, statistically speaking or probabilistically speaking, that the probability of having one question that's anchored would actually even be very close, in some type of absolute value, little L1 norm distance with regards to setting both of the questions to being anchored conditionally, again, upon the fact that the players are winning across all of the coordinates. And again, this is just relating to statistical condition that not only do we want, like we have been mentioning, the absolute value distance or the little L1 norm distance to be approximately zero, namely the fact that maybe more often than not, probabilistically speaking, these two discrete events, conditional probabilities are roughly, occur roughly with the equal or occur roughly speaking equally with the same chance, but also that this is actually going to allow us to further formalize dependency breaking variables and how this can be seen as some type of quantum version of symmetry breaking that we see in classical matter, which is again why I really felt that was informative to bring up again those previous works of mine in statistical physics and how this is again we're going to build up the interpretation from a quantum information processing perspective of removing some quantum correlations from the system and determining what would be the accompanying or the corresponding impact on the players being able to satisfy the referee scoring predicate and hence being able to win the game. And again, so this is the set of multiplayer dependency breaking variables given by omega multiplayer, which is given by identically being equal to some union of little omega and big omega, where little omega is a dependency breaking variable over position J. So we can pretty much have the dependency breaking variable act along any type of position J corresponding to some round or some fixed round at parallel repetition and determining whether changing the dependency breaking or whether applying a dependency breaking variable at this position and hence for some fixed round of parallel repetition in some type of multiplayer game with an arbitrary number of players or participants would actually significantly decrease the winning would it significantly decrease the winning probability or not? And the space of all strategies is given by the fact that it's script n, which is identically being equal to the space of all script sub n in the cursive sub n, where each one of the strategy script sub n is given by the fact that the intersection of the two following probabilities, namely the first probability that the players can win using script sub n, additionally given the fact that each one of these product strategies, little script sub n, which is an instance of the cursive sub n, satisfy the usefulness and the sampleability properties simultaneously, both being strictly positive. And in this presentation of the series, I'm not going to just yet, immediately define the usefulness and the sampleability properties. I'm going to define those in the next presentation of the series. But pretty much they're two very intuitive conditions which are outlining basically the circumstances under which Alice and Bob or an arbitrary number of players in a multiplayer game theoretic setting can make use of entanglement so that basically even if some instance of dependency breaking is or a dependency breaking variable is applied, again, like we've been describing, at some fixed round of parallel repetition for a game, that they would still be able to win with high probability. And so basically, these are some types of conditions which have been studied throughout, many different cases in the literature, but also many researchers who had studied it for the two-player games and other types of related game theoretic settings had really been discussing and mentioning about how it would be very interesting to be able to make some make sense of some multiplayer game theoretic analog of this version, which we're describing now. And the set of all product strategies is coming into play because obviously, given the fact that we're talking about parallel repetition and there's some type of factorization of the optimal value in terms of taking a product over the optimal values to determine the rate of decrease of the optimal value under parallel or strong parallel repetition, it's really important to be able to look at, namely, the set of big wedge, this wedge operation corresponding to the parallel repetition operation, which is given by cursive S raised to the J, where J is over where the parallel repetition operation is taken over little n, namely the total number of parallel repetition operations or the rounds in which a game is repeated in parallel, and how this can identically be expressed in terms of the product over little j of the same set of all strategies, which is identically being equal to the product over little j, again, between 1 and little n inclusive, where the strategies kept psi raised to the j, in which the players participate using this strategy for each instance of parallel repetition of whatever multiplayer game theoretic quantum game they're participating in, and they're receiving and responding to questions drawn from the referee's probability distribution. In the Bell states and the EPR pairs, as in the two-player game theoretic quantum setting, they really come into play because it's the model system, so to speak, of entanglement, or just basically the simplest system in terms of quantum physics in which entanglement occurs. And this is really given by the fact that it's given by each one of the operations, it's given by a tensor product of two components. We can either look at the sigma x or the sigma z components, which correspond to Pauli basis elements, as well as the identity operator. And we can just see that what we're acting on with these tensor product operators is given by the fact that we're looking at some type of superposition. Sorry, I just want to open the window a second. It's kind of hot in here. Sorry about that. Yeah, and what we basically want to do in looking at these tensor product operations is given by the fact that we're looking at acting on a superposition of either 0, 0, and 1s, however many zeros and ones there are players, normalized by square root of 2. And basically, the Bell states and the EPR pairs, which are given in terms of some system for entanglement, are given by the fact that we can either obtain some type of very simple superposition, which in the first case of the identity of the tensor product between the identity with itself, it's just the state that we originally got. Or if we're looking at the sigma x, one of the polybasis elements, which is tensor product with the identity multiplied by the same state, we're flipping the occurrence of zeros and ones. Or then if we're looking at sigma z, a tensor product with the identity, we're reversing the direction of the second state in the superposition, as well as given by the fact that for the final tensor product, we're looking at sigma x, sigma z tensor product with the identity, which is given by the fact that we're simultaneously switching the sign of the second product, of the second term in the superposition, in addition to also interchanging the order in which zeros and ones occur. And the probabilities of sampling the multiplayer dependency breaking set variable set are of great interest for us to continue formulating and actually, again, determining how this relates to the condition of winning across all coordinates, which is corresponding again to being able to have a sufficiently high winning probability of winning across all rounds of parallel repetition for some type of multiplayer game theoretic setting. This is given by the fact that what we're looking at is we're looking at the probability of sampling a multiplayer, a dependency breaking variable set conditionally upon the fact that we're also looking at some boldface x occurring where each one of where this boldface x from 1 up to n, big N, namely for an arbitrary number of participants, is given by a union over the number of players, which is related to the responses from each player to questions drawn from the referee's probability distribution pi. And what we're saying is that this conditional probability, which is dependent upon sampling the multiplayer set of dependency breaking variables, can approximately be equal to actually removing one of the instances or one of the answers for the nth player in setting that identically equal to little y, as well as performing accountably many number of ways or similar procedures to the questions that are received from, or the questions that are sent to each one of the players from the referee's probability distribution, leading namely from y, including y prime or y prime 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 with an arbitrary with n minus 2 dots in between the primes and the superscript of the question, which is very much relating upon the fact that it's having a very similar effect in a probabilistic sense in terms of removing quantum correlations from a system like we had discussed in the first probabilistic condition that we were beginning in this presentation, namely the fact that we can set some of the questions which are distributed to each one of the players to some anchoring, which statistically speaking, we would hope that with respect to the little L1 norm or the standard absolute value distance between probabilities, that these probabilities are roughly equal to the same, which would then allow us to determine how some smaller or some more local changes to the quantum strategies can actually maybe be used to accumulate and to introduce questions across a broader range of questions that are distributed to these players and to these participants from the referee's probability distribution, which would then maybe constitute some symmetry breaking or some dependency breaking and could maybe potentially have some impact, some significant impact on the winning probability. And as stated in the first slide, like we've been mentioning, one can perform similar procedures for anchoring questions corresponding to the probability of sampling the dependency breaking variable set. In fact, the multiplayer dependency breaking set. So this is again just given by the fact that we want to look at and be able to quantify the conditional probability of sampling the multiplayer dependency breaking set conditionally upon the fact that boldface x of with this subscript being between 1 up to big N, corresponding to all the players, is equal to some some collection of n questions which are distributed to each one of the players from the referee's probability distribution uniformly at random, also conditionally upon the fact that we're winning across all of the coordinates, all of the instances of parallel repetition. And again, we can see that this statistical type of assumption that I described in terms of the probabilities before we introduce anchoring and after we introduce anchoring being roughly the same is given by the fact that it's pretty much appearing in a very similar type of circumstance here, because what we're saying is that basically if we remove a question that's distributed to the nth player and set it equal to y, or even we do this for countably many players or even all the players, this probability of sampling the multiplayer dependency breaking variable set should be roughly the same. Also conditionally upon the fact that we leave the conditioning of winning across all the coordinates to be identical in all of these conditional probabilities. An expected outcome from previous work due to anchored parallel repetition of Bavarian, Vidic, and Ewan. They really have a lot of great papers, which I've provided in the biography for each one of these videos, just basically describing the fact that we want to determine whether their conclusions for two-player expanded games can actually be used to infer some type of good probability of sampling the multiplayer dependency breaking variable set under under anchoring, basically also given that they're still winning across all of the coordinates. And again, this is just given by the fact that I haven't exactly described what the differences are between multiplayer games or other two-player game theoretic settings and expanded games. That's kind of more, that's not necessarily something that I felt was the most informative to do at this point. But it's just helpful to at least think about maybe some settings in which multiplayer dependency breaking variables for expanded games can come into play and can be related to other multiplayer games, which is in fact what we're trying to study, because we're basically determining whether the probability that sampling the expanded set of dependency breaking variables for different types of quantum games, conditionally upon the fact that we're setting the question that's distributed to the first player from the referee's probability, conditionally upon the fact that they're winning, W sub C is approximately equal to, or is, again, very close to, in a statistical sense, with regards to the little L1 known in the absolute value distance, for actually also conditioned upon the fact that the question that's distributed to the second player from the referee's probability distribution is identically equal to little y. And whether this, again, this statistical assumption and this closeness with respect to the standard absolute value norm of these two probabilities for sampling the expanded set of dependency breaking variables would imply that a similar type of result would exist for the multiplayer dependency breaking variable set. So that's very much like the type of perspective that I was trying to think about in terms of using the two-player game theoretic settings as I have in other types of work to build up some more type of complicated interpretation, either through error bounds or generalizations of error bounds, and how that relates to several multiplayer game theoretic settings simultaneously at once. And this is just again given by the fact that, as we have been describing in the previous presentation or the previous slide of this presentation of the series, that we really want to be able to look at said introducing some anchoring. Say we're introducing some anchoring for the n-1th player and the nth player, and then how that can be related to the anchoring of just the nth player of the question that's distributed to the nth player who's participating and who's one of the agents and players in this multiplayer game theoretic setting, which would then allow us to basically cascade this impact or cascade this effect of anchoring for all the questions are distributed to all players to determine what would be the expected result and the expected impact on the optimal value, hence upon the maximum winning probability of the game. And again, generally speaking, as we've been describing more of these types of objects and these quantities and building more of the interpretation up from quantum dependency breaking and how that relates to standard classical dependency breaking in condensed matter and related types of areas of statistical physics, is that we can have two possibilities. Namely, we can look at the probability that there's some set of all variables, excluding the dependency breaking variables, for which the cardinality of the multiplayer set of dependency breaking variables in comparison to the set of all dependency breaking variables are approximately equal, namely that the cardinality of these two types of sets through this ratio that's given in the first probability on the slide would be approximately 1, namely that their cardinalities or the total number of variables in each one of these sets is approximately equal. Or one could have another type of possibility in which we're looking at for all sets of variables, there exists some C, which is a strictly positive quantity, strictly positive parameter, for which roughly speaking, the set of multiplayer dependency breaking variables would be I think sorry, I think that this should this should point the other way, which is why I do some of these presentations sometimes to catch little typos. But I think the inequality should be reversed the other way because basically it's communicating the fact that basically there are much fewer dependency breaking variables than there are variables that players can use for being able to remove or being able to observe decoherence amongst their quantum strategies. And obviously, given the fact that probably the cardinality of the dependency breaking variable set is not very comparable to the cardinality of just the set of all variables that players can use, we're going to be describing more with regards to why the assumption of the second item on this slide is more realistic and how that's going to demonstrate how we can formulate conditions in probabilistic computations with regards to dependency breaking and symmetry breaking. And the collection of tuples under anchored parallel repetition takes the following form, namely, we're looking at some set of coordinates big C, which is given by identically being equal to the decomposition over all coordinates little I, which in itself can identically be expressed in terms of a union over all coordinates little I with tuple C, where each one of these tuples have finitely many coordinates corresponding to the number of rounds of parallel repetition that we're performing. And we can compare optimal values through the following probabilistic statement, namely that if we're looking at some game G, it can be either a two-player quantum game or multiplayer quantum game. We're looking at the probability that for all omega of G greater than omega prime of G, namely where omega and omega prime of G, they can denote different types of supremum or maximum winning probabilities given different collections of strategies that players can use. There exists two quantum states, psi prime a multiplayer and psi a multiplayer, such that omega prime of G is proportional to psi the bra of psi multiplayer given by the which also has the components or the contributions of a tensor product over the number of players times ket of psi multiplayer, which is stochastically dominating which is stochastically dominated by the expectation of value of bra psi multiplayer uh, multiplied by the tensor product representation over the number of players of the tensors of player observables, and ket psi multiplayer, which is proportional to omega of G. So this is just basically determining and really illustrating how restricting or putting conditions upon the number of strategies or the total number of strategies within an arbitrarily large combinatorial space that we can actually consider that the players can use for participating in the quantum game will directly impact the optimal value. And the action of the dependency breaking set of variables is given by the following condition, namely the fact that if we're looking at the action of dependency breaking variables across all instances or all coordinates, which is corresponding to individual rounds, like we've been mentioning, of the parallel repetition operation, and determining, again, being able to quantify how the optimal value of the game would decay, whether that decay would be exponential or not, is given by the following set of conditions, namely script D of B, namely the set of the action associated with omega multiplayer, the set of dependency breaking variables along each one of the coordinates is identically being equal to the action of the across all of the coordinates, which is identically being equal to the action across all of coordinates I prime, say for other instances in which we're looking at maybe some other type of some other type of number of parallel repetition operations, which is identically being equal to the action of the dependency breaking variable set across C prime. So this is just pretty much to say that even if we look at coordinates and we index them in different types of, and we index these coordinate sets in either I or I prime, it's pretty much amounting to still looking at parallel repetition of some fixed number of times and how this is actually relating to our ability to quantify whether the winning probability would be substantially decreased or would substantially change or experience some transition from what the probability was before we were applying dependency breaking variables with this type of associated action in the first place. And the multiplayer XOR biases is given by the fact that it's very much related to the previous types of expressions that we provided in the previous presentation, the first presentation of this series for the two-player bias, because pretty much it's given by psi sorry, bra of a psi 3 XOR, 4 XOR, 5 XOR, n XOR corresponding to multiplayer XOR games, as well as given by the fact that we're still having this tensor product, which is dependent upon either the first three questions that are distributed to the players from the referee's probability distribution, or the 4 questions or 5 questions or an arbitrary number of questions given by big N, as well as the remaining state kept psi 3 XOR, kept psi 4 XOR, kept psi 5 XOR, or kept said n XOR, respectively. And the multiplayer question set is given by the fact that we're looking at being able to look at the question set for the 3 XOR game, the 4 XOR game, or the n XOR game, in which in each one of these instances, for each one of these multiplayer XOR games, we can identically express it in terms of a union identically being equal to a union over little q1, little q2, little q3 of the union of big q1, q2, q3, or a union over 4 elements, or a union over an arbitrary number of elements, n elements, big N elements corresponding to n players in the multiplayer game. And we're also going to be making use of in upcoming presentations in the series, a couple of tools from quantum information theory. And what these tools actually relate to is, first of all, the little L1 distance between two quantum states. We had kind of been mentioning this before, but it's just basically the trace of the absolute value. Namely, if we fix two quantum states rho and sigma, the L1 distance is equal to, namely, the L1 norm with two bars that is given from this norm, which is identically equal to the trace of the representation of the complex conjugate of rho minus sigma times rho minus sigma, which is identically equal to just the trace of the absolute value norm, the L1 norm between rho and sigma, as well as even being given by the fact that we can look at being able to introduce a second tool from quantum information theory, which is relating to the fidelity between two quantum states. Namely, with the same two states rho and sigma introduced in the previous item, the fidelity is denoted by f of rho and sigma equal to the L1 norm of the square root of rho times the square root of sigma. And the Fuchs-Van der Graaf inequality states that 2 times 1 minus the fidelity between rho and sigma is sandwiched in between, or is less than or equal to the L1 norm between rho and sigma, as well as this L1 norm being upper bounded by less than or equal to 2 times square root of 1 minus the fidelity. And finally, the data processing inequality, which has many types of applications in quantum information theory and quantum information processing, is given by the fact that if we have some quantum channel script E, which now the viewer can understand why I was kind of belaboring and talking about some aspects of quantum channels and how to distribute and encode and authenticate and transmit classical information over quantum channels, is because it appears with this data processing inequality in this condition from this tool of quantum information theory. And namely, it states that if we distribute the two quantum states rho and sigma over the quantum channel, the norm, not the L1, not the little L1 norm, just the norm between epsilon of rho minus epsilon, or E of rho, E of sigma, is upper bounded by the L1 norm of rho and sigma. But there are some remaining conditions relating to the data processing inequality, as well as given by the fact that the fidelity of E of rho and E of sigma is strictly bounded below by the fidelity of rho and sigma. So namely, the fidelity actually of transmitting these two quantum states over the quantum channel epsilon is actually increasing, and is a monotonically increasing function as we transmit these quantum states over a quantum channel. And really, the above inequality for data processing can be straightforwardly be indexed with respect to the number of parallel repetitions, little n, namely given the fact that we're looking at indexing rho and sigma with I, where I is an index for the number of operations that we're applying this wedge operation, namely the parallel repetition operation, which is identically being equal to E of rho of 1 up to little n minus E of sigma of 1 up to little n, which is less than or equal to the absolute value norm of rho of 1 up to little n minus sigma of 1 up to little n, which is identically being equal to the parallel repetition operation for I between 1 and little n inclusive of just the norm distance between rho I minus sigma I. And objects that will be further discussed throughout the remaining presentations, which I felt like it was very great to continue discussing and to formalize more concretely now, is that we're looking at these following 9 items. So I'm just going to spend a little bit of time just again hammering in this notation and further emphasizing this notation and how it's really been appearing in this conditioning or other aspects of the discrete probabilistic events that we're trying to be able to quantify and how that relates to quantum correlations and how we can observe decoherence or potentially ways to break quantum correlations through anchored parallel repetition. And this is given by the fact that the first quantity which we're introducing is a dependency breaking variable at position I, namely we're fixing some tuple or some position I within the coordinates C within the set of all coordinates big C, which is actually allowing us to determine, again, for some instance of parallel repetition, what would be the impact of applying a dependency breaking variable at this position with regards to removing correlations and maybe impacting negatively the probability that the players can win some game, which again is being satisfied, which we're determining is being won or not according to the referee scoring predicate. And again, the second and third item, which we're describing is X sub C and Y sub C, namely the set of all questions across all rounds of parallel repetition, which are distributed to the first and second player, which again, in the two-player setting, the typical archetypical agents and players are given by Alice and Bob. And again, this is given by the fourth and fifth item, which is saying the first player's answer is given by A sub C across all the coordinates. And sorry, that's another typo. The second player's answer is given by B sub C across all coordinates. And then in the sixth item, the set of all dependency breaking variables is given by omega being identically equal to a union over all of the coordinates n, which are belonging to which are not belonging to C, given by the fact that we're unioning X sub C and big sub C. So what this is having the effect of doing is saying that we're leaving some of the questions that are distributed to the players from the referee's probability distribution fixed, while we're leaving open the possibility of being able to allow dependency breaking variables to be applied to all other coordinates for all other questions that are distributed across different rounds of parallel repetition from the referee's probability distribution. And relatedly, in the seventh item, we formulate how to basically describe dependency breaking variables for some coordinates away from I. And then the eighth and ninth object are basically determining that we're looking at a way to formalize the set of dependency breaking variables, namely the set of omega appears in each one of these quantities, in addition to A sub C and B sub C in each one of these quantities, namely the fact that when we're looking at little I in the second expression for the dependency breaking variable set, we're conditioning upon the fact that there are some coordinates that we don't want to apply dependency breaking on because we're looking at how dependency breaking would occur at some position in away from this fixed position amongst all other rounds of parallel repetition. In a previous derivation of upper bounds due to Jain and Kundu, another previous work that I described in which they very much also seek to generalize and provide some other type of maybe higher dimensional multiplayer game theoretic interpretation of the results that are offered in the reference I've been describing from Bavarian, Vidic, and Ewan, is that they relate the upper bound of a system of a probabilistic system that's going to be related to the system of expectation values, which I'm going to introduce in other presentations and other arguments later in this series in terms upon the one side anchoring probability C, namely given by the fact that the probability of sampling X sub I, Y sub I condition and some instance of dependency breaking at position I conditionally upon some encoding is given by the fact that we can subtract this from minus the probability of X sub I and I sub I minus or also multiply by the probability probability of R sub I, but also adding some conditioning in terms of the encoding at the ith position, which we incorporate and enforce for the question that's distributed to the second player or to the second participant in the game, which the L1 norm, the little L1 norm, namely the same type of statistical absolute value distance, which we had introduced earlier in the presentation in this series, is bounded above by 7 over 20 times the one-side anchoring probability. And also, similarly, as one could expect, a very similar type of probability, which is given in the second type of item, given the constraint that C, the one-side anchoring probability, is between 0 and 1, because it's a probability that could occur with a probability 0 or 1 by a 0-1 law, like what's been described in seminal work in probability from Kolmogorov's 0-1 law, is given by the fact that this has the same upper bound, namely 7 over 20 times the one side anchoring probability. And finally, for the third item, which is given in this system of probabilistic quantities, we're actually having an expectation value, which is very much similar to the types of expectation values at which we're going to be describing, in which we're looking at the outer product between psi corresponding to some strategy that players can use, which is subtracted from the minus of that minus of the tensor product of the identity tensor product with some unitary corresponding to the ith player, as well as basically reversing the direction of this inner product of this outer product and inner product, which is also multiplied by the complex conjugate of just the unitary, which is also a tensor product with identity, that the L1 norm of this expectation value is upper bounded by 21 times the one-side anchoring probability. So this is very much a very similar type of statement, which is going to allow us to determine what are the limitations of information processing and how this will actually relate to multiplayer game theoretic settings in anchored parallel repetition. And so it shouldn't really come as a surprise that we're going to introduce expectation values of the following form. So we're going to introduce expectation values over all possible positions little I, in which one will want to upper bound this type of probability like I described in a previous slide, namely like the probability of x sub I sampling upon some instance of dependency breaking at position I, given some encoding, minus subtracting the probability of y and y sub I, r sub I, given the script E, multiplied by the probability of sampling x sub I conditionally upon y sub I. And we can also look at expectation values which are normalized in the anchoring probability, namely upper bounding the expected value of the outer product of the quantum state corresponding to the success probability under the action of projection operators in comparison to the outer product, which is basically given by the fact that we're looking at, again, an expectation over little I, as well as looking at an expectation taken with respect to the probability measure of x sub I, r sub I, given some encoding of 1 over alpha, where alpha represents the anchoring probability of the L1 norm of this very similar type of expression which we had provided in the previous slide, namely, instead, we're looking at the action of some projection operators which are dependent upon all of the questions which can be drawn from uniformly at random from the referee's probability distribution, as well as some instance of dependency breaking at this same position from the questions that the referee distributes, which are acting upon this outer product of psi and psi prime, as well as subtracting off just the outer product of psi. So basically, psi and psi prime are just basically two types of representations for different quantum strategies that players can use. And the anchoring probabilities are defined through the following types of quantities. So recall from the beginning of the presentation that I described to the viewer how basically we introduced this LaTeX bot symbol, which is allowing us to just basically introduce anchoring for some questions that are drawn from the referee's probability distribution that the players are going to be responding to. And this is pretty much demonstrating the probability mass function corresponding to anchoring for each one of the n questions, which are drawn from the referee's probability distribution. So it's pretty much just given by the fact that each one of these probabilities, boldface P, given a measurement, given some outcome of the first player responding with the question script A sub 1, script A sub 2 for the second player, and so on and so forth for the nth player, script A sub n. is given by the fact that we're either taking the probability with the support of this probability measure being over script q sub 1 of being able to sample little q sub 1, which is normalized by 1 minus eta, where eta is given in terms of being equal to alpha over 2, namely 1/2 of the anchoring probability, which is equal to this probability mass if and only if the first question is not an anchored question, or otherwise being equal to alpha sub n, alpha minus eta sub n over 1 minus eta, if and only if the question that's distributed to the first player is anchored, and so on and so forth for the remaining participants and the remaining questions that are distributed to these players in the game from the referee's probability distribution. And the anchoring probability corresponding to each one of the players is defined as follows. So this is just saying that when we're looking at the probability measure and the support being over script q sub 1, given the fact that the answer with the first player is anchored is identically being equal to the fact that we're looking at the probability with respect to the support of the questions that are distributed to the first player, that player 1 responds with an answer from the anchored set is identically being equal to alpha. And we can introduce this same type of anchoring, being namely setting all these other probabilities equal to alpha for the responses from the remaining players and the remaining participants in the game. And the computations for upper bound of the POVM system are dependent upon the relative and the relative min entropies, namely the fact that we're looking at some expectation with respect to some probability from the answers of, say, 3 players by making use of the dependency breaking notation given in the paper by Jain and Kundu, in which we had described from a previous slide how they had obtained and derived some upper bound for some system of probabilities and expected values, which are dependent upon some fraction, some fraction 7 over 20 and also 21 of the one side anchoring probability, which is very much relating to the following computations with the relative min entropy. Namely, we're defining state 1 and state 2, which are relating to some suitable unitaries, which players 1 and player 2 in the game can make use of for this information processing task, and how, in fact, the relative min entropy can be expressed in terms of the expected value of S infinity between state 1 and state 2. And the relative min entropy, S infinity, is defined as given two quantum states rho and sigma being the minimum over lambda for which rho is less than or equal to 2 to the lambda times sigma. In two-player settings, state 1 and state 2 are defined through the following traces, namely state 1 is given by the trace of some unitaries that Alice uses, given by the tensor product of theta and sigma, or any two quantum states which we're using, as well as the Hermitian conjugate, as well as state 2 being equal to a very similar type of expression. And we can generalize computations in a type of straightforward way, which I feel is very helpful to at least describe more in this type of presentation of this series as we've been discussing multiplayer dependency breaking variables, because it allows us to generalize computations for entropy in multiplayer game theoretic settings, in which basically for the multiplayer setting, one argues that we're going to look at an expectation with respect to some probability distribution, where the probability distribution is over the possible questions that can be distributed to each one of the arbitrary number of participants and players in the game. Pretty much the relative entropy of the multiplayer state 1 with multiplayer state 2, which can pretty much be identically be equal to the expected value of just the relative entropy, which in turn can be strictly upper bounded with the expected value of the relative min entropy S infinity of multiplayer state 1 and multiplayer state 2. And pretty much state 1 and state 2 and all these other states, which we can straightforwardly define in the multiplayer setting, is given by the fact that we're still looking at the conjugation type of action from player unitaries, but it's given by a tensor product in each one of these traces for state 1 and state 2 respectively, which are given by theta sub 1 up to theta sub m and theta 1 sub prime up to theta n sub prime. And unitaries for each of the player in the multiplayer setting are defined as follows, namely the player unitary is given by the product over all the unitaries between 1 up to big N and inclusive, as well as being able to straightforwardly define the complex conjugation action of the player unitaries component-wise over all little I. And one performs computation with entropy from states of the following forms, namely the fact that, again, we're saying that we can define the remaining states, state 3 up to state big N, in terms of a third player unitary or an nth player unitary, and taking just basically tensor products between these states. And yeah, sorry, I forgot these dashes in between there, but there should be additional dashes for the states which we're taking the trace of under the unitaries for the nth player. In computations with the relative min entropy, you can express as a summation over the number of players shown below. Namely, we're taking the expected value with respect to some probability measure of taking a summation of S infinity of the I minus 1 with the I state, which can be identically expressed as the summation over the expected value with respect to the same probability measure over the questions distributed to each one of the players of the relative min entropy S infinity between the I minus 1th player set and the ith player set. So this is again reiterating how we can cascade and pull through contributions from the relative min entropy for being able to quantify the impact of anchored parallel repetition on the optimal value and hence upon the supremum or the maximum winning probability. And so the conclusion that I wanted to end up this presentation with is that we introduced more objects related to anchored parallel repetition. We established points of comparison between previous work of the author and me in several multiplayer game theoretic settings. And we describe how anchoring probabilities in several closely related objects are defined for multiplayer anchored parallel repetition. And finally, we began alluding to more arguments which will be described in upcoming presentations of the series for multiplayer anchored parallel repetition. And thanks for watching.